All right, so welcome back to my stream. Again, my name is Joey. I'm going to be your math teacher for this upcoming hour session. Again, we've been going along through, if you're joining us for the first time here at OneClass, what we're doing is we're going through frequently asked questions in both the secondary and college and university level in specific subjects such as math and chemistry as well. So what we're doing is we're compiling questions that you've asked or you've answered. Sorry, you've asked more so. You've asked us as Googled or asked throughout basically these subjects, and we've compiled them to a document. And what that document does is we pick questions through that that pertains to subjects that we are currently working with. So that's what we're doing now. And sorry, and and while we do that, basically, while in the process of that, how we are working, what we're doing is we are compiling these questions, we are answering them for you, and we are going to teach you the concepts through that question, and then and we're going to kind of walk on this journey together in terms of verifying solutions and making sure solutions are correct. So that's kind of my responsibility for this position here. Again, my name is Joey. I'm coming from a background of being a teacher. Again, I'm a secondary school teacher in Ontario, and my specialized subjects, are in math and in chemistry and music as well. So these are my specialized subjects, and yeah, so that's kind of the background I'm coming into this with. So without further ado, let's go and get started on these questions. Again, I picked these questions more so because in the previous stream we did more so grade 11, grade 12 math. This is now simply just grade 9 and grade 10, or maybe some geometry questions as well as some algebra questions as well. So let's get started on the first question here. All right, so we have this question here. It says, what is the simplest radical form of 53? So simplest radical form, I think, is it square root of 53 they want to say, or I think it just means 53. Let me just assume 53 here. So it says, what is the simplest form or radical form of 53? So when we talk about radical form, again, how we would reduce something is if you have radical form like this, if you had like something like a square root of 49, for example, that would equal 7, right? Again, 7 squared would equal 49, right? So or 7 squared would equal 49, right? So basically, again, we know how to do, we know how to break down radicals to specific things, right? But what we have here is we have a whole number, it's 53. So when we talk about what is the simplest radical form of 53, how we can kind of approach this problem is by using we can actually just simply square the number. If we square the number of 53, we actually get a radical. We get a radical number, right? So for example, let's do this in blue. So for example, if I have 53 here, and I want the radical form of 53, if I take 53 and I square it, what that would give me is, let me take out my calculator, 53 squared. So it's simply 53 times 53, right? That'd give me 2,809, right? So this here is 53 squared, which means, therefore, if I take the square root of both sides, so if I take the square root of 2,000, so if I square root 53 squared, that means if I square root both sides, 2,809, this here is 53, right? This is 53, these two cancel out. Square root of 2,809 is 53, right? So therefore, that means the simplest radical form here would be kind of 2,809 is the simplest radical form, right? Because I know that the square root of 2,809 equals the whole number 53, right? So again, that could be by radical for this problem. So I'm going to look at the what they did here. Okay, so this is weird. Okay, hold up. Okay, so they actually assumed this is the square root of 53. Okay, so this changes the problem now. So let me just redo this. So they're assuming that it's the radical form of root 53. Okay, so that actually changes the problem. So this here is not my answer here. So this here was for the whole number 53 and not square root of 53. So let me redo this problem. So how I would do this problem is, again, I would have to look at 53 here. I can think of it as I'm trying to think of what are the factors of 53. So let me just think about this in terms of factor of 53. I don't know if 53 is factorable. Let me just check. I don't think 53 is factorable. So when we talk about simplest radical form, this is actually like 50 square root of 53 in itself, because I don't have any factors. 53 here is a prime number, right? This here is a prime number. I actually can't break that down into specific factors in order for me to find the simplest radical form. So this here is simply just root 53, right? I can't break this radical down into more parts. However, what we can do is you can actually sub into square root 53 and you can find it on a calculator. It equals like 7 point something, right? And basically I think that's what the solution they did was here, right? They did some sort of they did a method-ass solution. So they're basically just dividing, they're taking basically the closest square root to this. So how they did that was they took if they know that 7 squared is 49, right? So square root of 49 is 7, right? So what they're doing is they're dividing this 53 number by 7 to hopefully get some sort of value. So that's what they did here. 7 times 7 is 49, and then what they did was they brought this down. You have 4, and then what that does is it's going to you're going to add 2 zeros here. You're taking the 2 zeros, and then you're solving for something else, and this here becomes 142 when you times 7 times 2 is 142 here. So that's what they're doing. 7 times 2 is 144 in this case. So that's what they're doing here in terms of simplifying that. But when we talk about simplest radical form, we want it to be in a true radical form, right? So we really don't want decimals. So when we talk about simplest radical form, it's simply just root 53. If you want to solve for like the decimal in itself, you would either use a calculator or you would use this solution here, which is correct. So basically what they're doing is they're plugging in 7 and they're figuring out by kind of like reverse division, like what the 2 decimal places are. So in this case, so that's what they're doing in these steps here. And with that being said, you get kind of 7.28 as as a square root of 53. So it's not an exact value, which I don't really like. I would actually personally just keep it at root 53, but this here is approximately 7.28 or plus or minus 7.28, right? So it's not a very like nice number in this case, but in reality, when we talk about simplest radical form, we actually want to place it in. We want to leave it within the square root of 53. We want to leave it in the 53. So this here, I'm going to say here solution is correct. Solution is correct, but when we are talking about simplest radical forms, we want to keep our square roots and not have decimals. So that's kind of what simplest radicals are, simplest radical form, because we want it to be we don't really want decimals in this case, so we can actually leave square root of 53 as square root of 53, and that's kind of the simplest radical form in itself. So I'm going to say solution is correct, because that's what they did in terms of they helped solve for the decimal place here. Okay, so it says here, this is a geometry question, or actually, I think it's more so a pre-algebra question. It says here, which of the following describes a rigid motion transformation? So this is 2. So which of the following so I'm talking about this concept of rigid motion transformation. So I have 4 options. I'm enlarging a photo, spinning a spinner, filling a tire with air, and slicing a log. So let me just visualize this for a sec. So enlarging a photo. So if I have this photo here, I have some sort of like, I don't know, like sun or something like that. And if I enlarge this photo, I would get something like, I would get a really, really big sun, right? Sorry, this is not a good picture. A big sun instead of a smaller sun. So I'm enlarging the photo. So in this case, if I'm enlarging the photo, does it actually change? Is it changing the motion of the? Is it changing a rigid motion transformation? Am I changing? Am I moving the plane? So in this case, I'm not, right, because again, if I'm enlarging a photo, it doesn't mean that I'm not changing anything in terms of I'm changing the actual dimensions of the photo, right? The sun here becomes smaller in this photo in A, and B here is a much bigger sun, right? So again, I'm changing the dimensions of the sun by enlarging a photo. So A here is not an example of a rigid motion transformation. B here, if I spin a spinner, so if I look at, I'm actually a pretty poor drawer, so I'm so sorry about that. But let me do some sort of maybe this is a fidget spinner of some sort. If I'm spinning a spinner or a top or something like that, am I increasing the size if I'm spinning it in, like, for example, the clockwise direction? I'm not, right? I'm only changing the distance between the center and the outside of the length of the spinner does not change, right? It's simply just rotating around kind of the center. So this is kind of a circle. It's going to rotate around this kind of circle here. So in this case, I'm not changing the distance. The distance will always be the same, right? The distance from the center and from the middle of the spinner to the center is equal at all of these points, right? Assuming it's a perfect circle. Again, it's not a perfect circle, right? But I'm assuming that these are all distances are equal, which means therefore this is a rigid motion transformation. So B here is actually correct. Let me show you C and D to prove that. That's right. So filling a tire with air. If I had a tire here, again, I'm sorry for my drawings here. If this here is a tire and I'm filling it with, I'm putting air, what I'm going to get is I'm going to get a bigger tire, right? The tire is going to enlarge and it'll have more air in it, right? So if I'm increasing the amount of the volume of the tire, then I'm increasing the distance, right? The distance between here, or sorry, the distance between the center and the end of the tire is, this here is smaller than this one. The center of the tire and this one is larger, right? Because it's more air in it. So it increases in radius, increases in diameter. So it means that this here is not an example of rigid transformation. And then D here, if I'm slicing a log, slicing a log into its sections. So again, if I had like a, oh my God, I'm so sorry for my drawing. If I'm slicing a log, if I'm slicing it by 1, 2, and 3 or something like that, the cross section, or not cross section, but this the cut of the wood would just be smaller, right? It would change the length of the log, right? Again, this here is one length here, is here, and this here, if I divide into 3 pieces, this is 1/3 of the length, right? So I'm changing the dimensions in terms of length, which means that the distance is being changed. So this here is not an example of rigid motion transformation. So this here is, so A is wrong, C is wrong, and D is wrong, which means B here is our correct answer. So let's look over here. So rigid motion transformation is also called isometry, and a term that describes moving the plane such that the relative motions of the points and distance stays the same, right? Again, here, this is an example that stays the same. There's translation, rotation, reflection, and glide reflection. And in this case, B here, it's a rotation, right? I'm rotating on the center here, right? I'm rotating, this is the pivot point, right? So enlarging your photo is not a type because all points change, good. Spinning a spinner is rotating, that's good. Filling a tire is not, because there's no such points which relative position can be found, because again, it's getting bigger and bigger. Slicing a log is not a rigid transformation because no property of rigid transformation. Yeah, there's no translation, rotation, reflection, or glide reflection here. So B here is the correct answer. So great logic and solution. So this here is a great solution, and my solution here is correct. So I drew it out because it's a bit easier to visualize, but this here is also correct as well. Okay, so that's number 2, I believe. Let's look at number 3. So it says every possible cross-section of a 3-dimensional figure is a circle. What is the figure? So think about that for a second. So cross-section of 3D shape, or every cross-section, every cross-section of 3D shape is a circle. And they're asking, what is the shape? What is the shape? So let's think about that for a sec. Every cross-section, remember, let's define cross-section. Remember, cross-section is, I'm taking the center of the point here of whatever shape is, and I'm cutting it by that shape. So for example, if I had something like a cube, I'm hoping I can draw this. I'm really bad at drawing here. Is that a cube? Yeah, something like that. And then if I'm taking the cross section, so again, the middle point here, I'm slicing it this way. I can slice it this way as well, and I can slice it this way, right? So there's 3 points. I'm slicing it 3 different ways. What shape would I get if I sliced a cube? Let me do this in blue. If I sliced a cube, so this is a cube, right? If I sliced a cube, I would get a square, right? I would get a cross section of a cross section of a cube. Cube is a square, right? Because all sides are even in a cube, right? So if I cut it in half and I cross it either this axis, or this axis, I'm gonna get a square, right? Or I would get a square in this case, in 2 dimensions, right? Because this is a 3-dimension, and I'm shifting it to a 2-dimensional shape. I would get a square. Same with the rectangle. If I cut a rectangular prism, I would get a rectangle. So if I cut every cross section of a 3D shape as a circle, what is the shape, right? It has to be some type of circular shape. It could either be a cylinder. Here it could be, what else? It could be a sphere. I don't know how to draw a sphere in 3 dimensions, so I'm just going to draw a circle. But those are kind of my options here. I guess a cone would also be fair as well, right? But again, my cross section of a cylinder here, I would have to cut it one way through this, right? 3 dimensions into 2 dimensions. In this way, one of these cross sections will be like a rectangle and a circle. One of them will be a circle, and then one of them would just be like a rectangle. If I do a cross section of a sphere, all of these ones here are a circle. And again, this sphere is correct, right? This sphere fits my definition, right? And then if I did a cross section of a cone, for example, I would cut it down right in the middle here, and to the side, and then cut one like that. I would get a very odd shape if I were to do a cross section of a cone here. So again, in this case, sphere is our correct answer, and that's what it says here, sphere, because if we cut the sphere using any plane, then the resulting cross section of a 3-dimensional figure is a circle. So that is true. So good solution and logic. So this here is correct. So that's number 3. Lots of geometry questions today. Let's look at number 4. So given RT, RT is congruent with WX, which statement is true? So it says here, okay, so let's let's break this down into 4 different things. So A is RT equals 2RX. B is RT plus TW equals WX plus TW. C here is WX equals 2RX. And D here is RT plus TW equals RW. Okay, so let's look at number 1. So number 1 states that RT equals 2RX. So let's look at RT here. RT is here to here equals 2RX. So RX would be from this point to this point here. So let me just redraw this trapezoid actually. Let me redraw this trapezoid. So this is R, this is T, S, X. This here is congruent, or let me do a blue. This here is congruent with this side here. This here is W. This here is V, and this here is U. Okay, so we have our 4 points here. So this is RT. So RT, so between this point, just in red, between this point here, and this point is 2RX. So between this point and this point here, RX, right? So from this point to this point. So if I bisect this this trapezoid, does that equal this? And in this case is false, right? Because I don't know if RT and WX is, I don't know if this point to this point is halfway through the trapezoid. So in this case, A is incorrect here, because I don't know if T is halfway through the trapezoid. And again, even if it was here, if it was halfway in this case, this total length here, because it's a trapezoid. So remember, if this here This here is my trapezoid here. There's two triangles here. I'm gonna have to take the length between this rectangle in the middle, and I would have to justify between this distance and this distance. So these two is not equal to 2rx. Let's look at B. B is RT plus TW equals WX plus TW. So RT, which is, let me erase this now. RT. So I know this is wrong. A is wrong. So I know that RT is this side here, and TW is this side from here to here equals WX. So from here to here and TW. So this here, this here. So in this case, B is correct. No one's perfect also says B is correct, and that's correct, right? Because I know that RT and WX are congruent with each other, and TW is the exact same like from here to here, right? DTW exists on both sides, right? So if you look at this algebraic equation, TW and TW are the same side, so you can actually cancel them out. And RT equals WX, and we know that RT here is congruent to WX, which means that this here is our correct answer. So B is our correct answer. I'm going to prove to you that the C is false too. So let me erase these guys here. So WX equals 2RX. So WX is here. And 2RX would be 2RX is from here to here, right? So from this point to this point. And again, I told you that if RT, this is the same, the A and C have the same logic here. It's still 2RX here, and RT equals WX, right? So this here is also false, right? Like I said before, well, if we bisect, or if this length from R to X is not 2 times WX, right? Because I know that, again, this here is a triangle here. This here's another triangle. I would have to justify for the length of the diagonal of the rectangle plus the length between the side to the tip of the triangle. So this here is incorrect as well. So it's the same logic as A. And then let me do D as well. Let me, oh shoot, don't want to erase that. Let me do D as well. Okay, so D here says that RT plus TW is RW. So RT would be this length here, TW is this length here, and RW would be this length here. So let me see, so this length here equals this length plus this, wait, R plus this length, right? So in this case, that's not correct, right? Oh, shoot. Can't even draw the triangle properly. So it says here, oh, actually, I'll do this in red, or blue, sorry. So RT is here, and TW is here, right? It has to equal RW, which is the red. So the blue has to equal the red. And again, in this case, this does not make sense, right? Again, I don't know anything about the lengths of these triangles. Even if it was a right triangle, I would have to have the format C squared equals A squared plus B squared, right? To solve for my lengths. So in this case, D cannot be correct also, which means B here is the only logical answer in this case. So no one's perfect. Awesome. Thanks for tuning in, by the way. So it says here, A is false, twice the length would be greater than the length. That's like we proved before. Option C is also false, and we said option B is correct, right? So we know that, and we can actually use algebra to kind of figure that out, because TW exists on both sides. So I can bring TW to one side. I cancel both of those terms out. I get RT equals WX, as stated before. D is also false. Consider the triangle RTW. RT plus TW is greater than RW, right? And addition of lengths of any two sides is always greater than the length of the third side, right? So exactly the same concept as if I had a, and this kind of has, I have any triangle here. Let's say this is 1, 1, and root 2. If I add these sides together, the horizontal and the vertical lines here, 1 plus 1 here is 2, right? And 2 here is greater than root 2. And you can prove that root 2 is like root 2 is like 1.4, something like that. So again, any two sides, addition of any two sides is always greater than the third side. So D here is also incorrect. So this here is my solution. B here is correct. This is great logic and solution. So this here is also correct. Sweet. So let's see where we're at now. So every cross-section RT. Okay, so we're at, this is now fill in the blank. A histogram aids in analyzing the what of the data. So this here is actually kind of vague because I'm not really given some background information, just says fill in the blank, which is kind of odd for a math question. So it's here, let's look at number 5. So a histogram aids in analyzing the blank of the data. So we have to, so again, this is like probably a pre-algebra question. Like we're looking at a histogram, right? So what is a histogram in the first place? So so instead of me drawing one for you, let me show you what a histogram is. So it's actually a lot easier to show you a histogram. So again, let's look at like this one here. A histogram, you have understanding my data, right? So it says here, this is actually give me a response time. Sure, let's use this one. This one's probably easier. There's no XX. Actually, I want an axis though. Let's see. Let's do this one. This one's easier. So tree heights and height, right? So I have these are the number of tree. Height is my independent variable, and then here is the number of trees, right? So how do we read this graph? We can say that our heights are in our independent variable, and the trees are dependent, right? So it says how many trees are between the heights of 100 and 150. Oh, this is about 5. Five trees are between these heights. Between 150 and 200, there are 30 trees that are between these heights. It's kind of like 25 maybe between 200 and 250. The greatest one here is 50, right? Most trees are from 250 to 300, and then from 300 to 350, it's about 10 trees, right? So again, we're showing basically number of trees using height, right, as our independent variable. So it says here, so it basically says it shows you kind of a distribution of your data, right? So basically it's saying here the histogram aids in analyzing basically the distribution, right? So it says here the answer says a histogram is a visual tool used to represent and analyze data, basically a graphic version of a frequency distribution, and it can show center, variation, and shape of distribution, right? So as you can see, let me reload my histogram here. I can see how sorry, I don't think you can. Oh, I can't. You can't see tree heights here because my face is blocking, but this says tree heights. I'm sorry, but you can see here there's a distribution, right? You can see less trees are basically from 100 to 150, and from 300 to 350. There are not a lot of trees there. The greatest amount of trees are probably in the middle, right? The average amount, right? So again, this is the distribution of the data. When we talk about, we'll talk about more of that in like statistics when we talk about in terms of the normal distribution, normal variation. We talk about kind of the confidence intervals and that sort of stuff. It's kind of mostly in stats here, but for a pre-algebra question, if we're just reading a histogram, it just says the distribution of the data. So I'm going to write here in analyzing, you can just say this is the distribution of the data would be a valid answer. You could say variation as well. That's a valid answer as well. This, again, it's a very vague question because we don't know what this student's trying to ask here, but this here is a great answer in terms of what they're trying to look at here. So great solution, and it's a good explanation. So that's awesome. So that's that question over here. So solution is correct. Okay, another geometry question for us here. Okay, this is number 6. So in the diagram, what must be true for point D to be an orthocenter? So again, what is an orthocenter? An orthocenter, and D here is the orthocenter, right? If I bisect the triangle between bisect this side, and from top to bottom, the lines at which they the point at which all 3 lines intersect is the orthocenter. So point D. So it says here, so which must be true for D to be orthocenter. So let me write down our solution. So A could be BE, CF, and AG are angle bisectors. BE has to be perpendicular to AC. AG is perpendicular to BC, and CF is perpendicular to AB. CBE bisects AC, CF bisects AB, and AG bisects BC. And then D here states that BE is a perpendicular bisector of AC, CF is a perpendicular bisector of AB, and AG is a perpendicular bisector of BC. So basically, it's the same thing as D. It's the same as C, but perpendicular bisector. Okay, So how would I solve this problem? What must be true for D to be orthocenter? So again, take a moment to think about this problem here, and maybe think of the word orthocenter. So what does that mean when we talk about the orthocenter of a triangle? So let me redraw this. Let me redraw the triangle here, and I'll show you what I mean by orthocenter. Recall the definition of orthocenter. So again, an orthocenter, if I have a triangle like this, is from this side, I have to take the center. So let's look at this side first in blue. So let's look at this first side on this side here. I have to take the center, and what that center point does is I'm going to have to make a 90-degree line like so. So this here has to be a 90-degree line for it to bisect my triangle. Same thing with the opposite side on this side. I have to take another line here, and this here has to bisect it in a right angle, and then from here to here has to be a right angle as well. So they all have to be a perpendicular. They all have to be perpendicular for us to construct an orthocenter, right? Because again, what you have to do is you have to actually extend. What you can do is you can extend these lines to make sure that this here is the orthocenter. Right? You can extend this to be a dashed line. This here can be a dashed line as well. This here can be a dashed line as well. So these all these lines have to be right angles of each other. Again, I drew my diagram I drew my triangle incorrectly here, but all of them have to be perpendicular to each other. So which means that A and C are incorrect answers, right? A and C are angle bisectors. Bisectors don't have to necessarily be a right angle, right? So this here, A and C are wrong answers in this case. And then we have B and D left. B says that BE has to be perpendicular to AC. And then B here is BE says it's a perpendicular bisector of AC, right? So when we talk about what's the difference between perpendicular and perpendicular bisector. So it says here, let me look at perpendicular first, right? So if I say something is perpendicular to each other, that means that I'm going to do this in red. That means that BE is this line here. So this here is BE has to be perpendicular to AC, right? So this here, these two lines have to also be perpendicular to each other, right? When we talk about a perpendicular a line here. So in this case, because BE is already because it says here it's confusing with the wording because it says BE is a perpendicular bisector of AC, and that's actually not correct, because what that means is if BE is a perpendicular bisector of AC, that doesn't make sense, right? I have AC here is just this line, right? From A to C is this here is a G. Sorry, this here is G. So it's AC is this line. Yeah, AC is this line here. So it's actually not, sorry, I wrote the wrong line. So it's actually this line here. So this has to also be a right angle here, right? Oh, sorry. I think I erased that. So this here is BC and AC. This here is also a right angle. But BE in itself is not a perpendicular bisector of AC, right? It's a perpendicular bisector of the triangle itself, so of ABC, right? So in this case, BE is a perpendicular bisector of ABC, CF is a perpendicular of ABC, and AG is a perpendicular of BC. So this here is actually tricky on the wording. So in this case, D is actually an incorrect answer, and B here is our correct answer here. So like they said, option B here is true, right? So why do we know B is the correct answer? Because BE is perpendicular to AC, right? As we showed from the orthocenter, this here. Or I guess this is here, this orthocenter, but BE in this case, BE here is perpendicular to AC, right? So this here is a right angle here, and that's correct, right? For point D to be orthocenter, that's a definition of that. But BE is not a perpendicular bisector of AC. AC, you can't really bisect AC, right? Like AC is simply just the line. I can bisect this. Bisecting this is not, it's not a perpendicular bisector, right? A perpendicular bisector of the triangle is BE. So this here is just a case of a wording here. So again, here it says that for the point D to be orthocenter, the only necessary part is BE is perpendicular to AC. They don't necessarily have to be bisectors of the side. So that, like I said, AC is not it's not like a bisector of ABC. So B here is the correct answer. So I'm going to say good solution and logic, because this solution here is correct. Sweet. Okay, so that's correct here. And okay, so let's see where am I in terms of. Okay, so it says here, what is the approximate height of the average adult in centimeters? So what number was this? This here is 7 now. This here is what an odd question. And I picked these because they're kind of pre-algebra questions. So maybe your classic grade 8, grade 9 questions here. But it's saying, what is the approximate height of the average, average adult in centimeters? So approximate height in I'll say height of average adult. Adults in centimeters. So cm. So when we talk about average height, we can't really mathematically solve this. This is simply just something we Google, right? So it's like simply like, oh, what's the height of an average adult? I would say, I don't know, maybe like 5'9" is a good kind of estimate here. So like 5'9". So again, I'm looking at the answer here. It says average height of adult men is 5'3" and 5'9". Adult women is 5'9" to 5'3". So let's say 5'3". So 5 or 5'5". Let's do 5'5". 5'5". So 5 feet 5 inches is our average average height. And again, this is the topic of unit conversion. We're converting units from this is from the empirical system into the metric system, is average height. So we have 5 foot and 5 inches, right? So in order for us to convert that, we have to convert that to inches first, right? Because we have feet and inches. I only want 1 unit first. So if I were to do that, again, I know that 1 foot equals 12 inches, right? So I can say that 5 feet over 5 feet equals, or I can multiply that by 12 inches. There's 12 inches per 1 foot, right? Which means I would equal this feet would cancel out. 5 times 12 here is 60 inches, right? So I have 60, and then I have to add my 5 here. So if I add 5 as well, so 60 plus 60 plus 5 is 65 inches. So I have 65 inches is the average height of our adult here. So now we have 65 inches. Now we have to convert inches into centimeters. So how do we do that? So we have 65 inches. And our conversion rate for centimeters here, it says it's 2.54, right? 1 inch is 2.54. You can also easily Google this and say inches to cm is simply 2.54. The formula is 2.54, right? And again, I'm not sure you have to memorize this. You might get a formula sheet for you to on the test for you to get that, so it's totally fine. But I'm going to say this is 2.54, and I'm going to use the exact conversion. This is centimeters per inch, right? Because there's 1 inch is 2.54 centimeters. So in this case, these units cancel out. So we do the operation 65 times 2.54 to give us our cm. So 65 times 2.54 will give us approximately 165 centimeters. 175.1 cm is our average height of our adult in centimeters, so 165. So again, this here is the concept of, again, unit conversion, unit analysis, something you kind of do in pre-algebra. So let's see here what they did. Hence the average adult. So they did the conversion right here between 63.6 and 70.8. I chose 65 in there. So hence the average adult men height in centimeters would vary between these two, and adult one would be these two. And I put 165 in terms of the higher end, so at 5.5, where centimeter is derived from the basic unit meter. So that's good. So again, this here would be a correct answer. Right? These I think it's a range. Right? I'm not sure what an average adult is. So, and I picked 5.5, 165 meters. My solution here falls in that range of the centimeters. So I'm going to say here is great range of solutions. Because the question was a bit broad when we talk about average height. I wish what they did was they showed the step-by-step analysis here. So I'm going to say here, I wish you showed these the unit analysis and conversion when converting from feet to inches and then finally to centimeters. But here is solution is still correct. So sweet. Okay, so that is number 7. Cool. Now let's do number 8. So number 8 says, how many sides does a hexagon have? Number 8. So it says, how many sides does a hexagon have? So again here, it's very simple, simple geometry. Again, take a minute to think about this question, and we'll take it up together, because we're talking about geometry, we're talking about sides, and we can also talk about angles here in this case as well. Maybe I'll extend the question and talk about angles as well. So take a moment to think about this problem here. How many sides does hexagon have? And what we can do is we can actually look at the prefix here, the word hex. What does the word hex mean? And what does the word gon mean, right? So again, if you have like so this is the concept of polygons, right? If we have a polygon is simply a shape with many sides, right? Many sides. The word poly means many, right? Polynomial means many variables. What else is a poly word? I can't think of anything. But polygon, shape with many sides, right? So the word poly means many here, and gon is just a shape, right? So and if we have a hexagon, then it's a shape with how many sides, right? So when you talk about hexagon, it would be a shape with 6 sides. The word, the term prefix hex means 6, right? So again, if you had something like a, let me think about, so the word triangle, for example. So let me do a side here in red. So shape minimum has to have 3 sides, right? Because it can't have a shape with a line. That doesn't make sense. It has to connect all their points, right? So a triangle has 3 sides, right? The word tri is 3, right? Think about tricycle, 3 wheels, right? So tri here is a 3-sided shape, right? Shape. A rectangle or quadrilateral, more specifically quadrilateral, I hope I spelled that right. Quadrilateral has 4 sides, right? The word quad is 4 sides. 4 means 4, right? 4-sided shape. Right, so all of these terms are dependent on their prefixes, right? And we can actually look at, if you want to look more at prefixes, what we can talk about. So this here is 6 sides, so that's the solution to the problem. But if we have a pentagon, the U.S. pentagon here has 5 sides, or a pentagram has 5. There's 5 sides to that. So hexagon has 6, and so this is the word pent is 5. Hepta would be 7, right? A heptagon will have 7 sides, and the octagon. So you can think of a typical, like if you're a UFC or an MMA watcher or a viewer, octagon has 8 sides, right? They fight in a 8-sided ring, right? So it has 8 sides. And then the next one here, if I want 9 sides, I would have something like a nonagon, right? A nonagon would have 9 sides. And then finally, a decagon would have 10 sides, right? 10 sides. So a decade, there's 10 years in a decade. Right? The word dec is means 10. So all these prefixes are actually really important. You're going to have to memorize a lot of these ones. So let me just highlight them again. So penta, you can think of pentakill as 5 kills, right? Or like pentagram, pentagon. There's 5, right? 5. Hepta is 7. We already did 6, right? 6 here is hexagon here. Octagon is oct. So it's there's 8 sides. Nonagon is 9. Decagon here is 10. So again, we have, these are all the prefixes, and it helps us define how many sides a polygon has. So these are all good prefixes. So let me look at this here. So a hexagon has 6 vertexes, cones, 6 sides, and 6 interior angles. So this here is even more specific here, and there's regular and non-regular hexagons. So let me just draw this out for you. And they're actually exploring angles as well. So let's look at this hexagon here. And basically, if there's 6 sides, what you can do is you can do something called the interior angles. So when we talk about interior angles, we're talking about the sum of interior angles in a polygon. So what we're going to do is I'm extending this question. I'm going to talk to you. Explain to you the concept of what that is. So the sum. So this, I'm going to do this in black here. So this is the sum of all interior angles. Sum of interior angles. So this would equal, you can think of it as n minus 2 times 180. So n minus 2 times 180. So what that is it means that my sum of all the angles, all these angles here. Oh, thanks for tuning in, by the way. So I have here, this is an angle here. There's an angle here, 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 and here. These are 6 angles, right? There's 6 angles. These are all interior angles. They exist inside the shape. So when we talk about sum of interior angles, what that means is it's going to equal, n here is how many sides the shape has. So this here would be 6 sides, right? I have 6 minus 2 times 180 degrees. 6 minus 2 is 4 times 180 degrees, which means 180 times 4 here is 720 degrees, right? So 720 degrees is the sum of my interior angles in polygon. And what I can do is, if I have a regular polygon where all of these sides are equal, so if I said that all these sides, so this is x, this side is x, 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 x. So again, all of these sides are equal, then all the angles have to be equal, right? According to the theorem, right? Where in terms of if all sides are equal, then all angles have to be equal for congruency, right? So if I have 6 angles and they all have to sum up to 720, what I can do is I can take 720, which is the sum of my interior angles. I can divide that number by 6 because we have 6 sides and 6 angles, and that will give me 120 degrees per angle, right? So all of these angles here, so all angles inside, individual angles are 120, right? So let me see, I'll write here, each angle equals 120 degrees. This is a regular polygon. So when we talk about regular polygon, it's all the sides have the same length, right? And then what we have is also we have a non-regular polygon where we have different sides, right? So if I draw something like, so this here is kind of a non-regular polygon, right? I have maybe this side here is longer than this side, right? So again, if I draw a non-regular polygon, again, the sum of the interior angles is still, so sum of I'll say int angles still equals 720. However, oh, this is a really bad 0, sorry. Just erase this. It still equals 720 degrees. However, not every angle is 120 degrees, right? So that means that not every angle, I can't divide it by 6 because not all the angles are the same, right? But however, it all sums to 720. So that I have a regular a hexagon or a regular, and this is the exact same thing for any other polygon, right? So if we had an octagon, for example, my n would equal 8, and I would get a different number for some of my interior angles. But for a non-regular polygon, again, my side lengths are not the same here. So again, that's kind of the difference between a regular and a non-regular polygon. So that's awesome. That's what they did here. Regular polygon has interior shapes, so they're all the same. Good. Non-regular hexagon looks like this. Like this is an irregular hexagon. I don't have 120 degrees for these angles here. So this is correct. So this here is great solution and logic. So that was number 7, I think. Or this is number 8. Number 8. Okay, number 8, and then number 9 here is this problem. So which of the following is the smallest prime number greater than 200? Which of the following is smallest prime number greater than 200? So we have A is 201, so we have this here is 201, B is 205, C is 211, D is 216. So right off the bat, what we can say is I can say that D here is incorrect, right? D here is an even number, so I can divide that by 2, which means that's not a prime number. Remember, the definition of a prime number here means that, so this prime number means that only factors are 1 and itself defines a prime number here. So 216, I can divide this by 2. Therefore, D is the wrong answer in this case. D here is not the correct answer because I can divide this by 2. So 2 is my factor. Okay, what else can I divide this by? I can see that B here is an incorrect answer as well because it ends in 5, which means I can obviously divide 205 by 5, right? Which means this here is also an incorrect answer. So all I'm left with is 201 and 211. So how do I figure out if there are prime numbers? So I have a little cheat for you. So what this cheat is, if I want to find out if something is divisible by 3, an odd number, what I can do is I have to figure out I have to add the specific digits up for me to figure out if it's divisible by 3. So for example, in 201, I have 2 plus 0 plus 1 equals 3. 3 is obviously divisible by 3, which means that therefore I can divide 201 by 3. So this here is also 201 is indeed divisible by 3. And you can actually check with your calculator if it is. I can type in 201 divided by 3, and as you can see, it gives me here 67 here. So that's just a little cheat for you to figure out if something is divisible by 3, which means B here is also the incorrect answer, or sorry, A is the incorrect answer, which means C here is our correct answer. 211 is indeed a prime number, and it is not divisible by anything. And if you have a calculator, you can check this. If I take the square root of 211 here, I don't get a simplified root here. So therefore, it is not a prime number. Sorry, therefore, it is the smallest prime number greater than 200. You could say maybe 207, but 207, 2 plus 7 equals 9. 9 is divisible by 3, therefore it's not a solution as well. So this here, C, is 211, which means this here is my correct answer. So C is also so C here is my correct answer, and it is my smallest prime number that is greater than 200. That's awesome. So this here, C is correct. So it says here, a number is a prime number if it has exactly 2 factors, 1 in itself, good. For example, 5 is prime number, and 1 and 5 are only factors of 5. Good. 10 is not a prime number, so they're showing examples, which is good. Now, 201 has at least 3 factors, 1, 3, and 201. And basically how they figured that out was they used my little cheat here, right? So again, let me write this cheat down. So if I have 201, what I'm going to do is I'm going to add the digits together, right? So I'm adding 2 plus 0 plus 1, right? So 2 plus 0 plus 1 equals 3, and then you take this number. Is 3 divisible by 3? If yes, then this entire number is divisible by 3. So that's how you do it. So you take the sum of digits, and you're going to check if divisible by 3, and that's what that is here. So in this case, A is incorrect. 205 has 1, 5, and 205. That's good. That's what I said here. Again, 216 has at least 3 factors. I said 2, but again, this probably has more, right? So again, 211 is the correct answer. So C here is our prime number here. So this here is a great solution. It's a great solution, and step by step. So sweet. So we got that. We got that solution down. So I don't know if that's my last question for today. Sorry, just give me 1 second. I'm gonna drag this here. Solution is correct. Yes. Okay. So this here is a repeat of the question I was asking before. So this here is was a repeat of the same question, and I just want to answer this question again because in our system it actually duplicated. So I'm just going to answer, and I'm just going to quickly verify and check if this solution is correct here, and that'll kind of bring us to our last question because it's again 12:55. It says here every possible cross section of a three-dimensional figure is a circle. What is the figure? So we did this question already. I'm just going to go back and check. So we actually did a lot of work today. So let me go back and check. We did this here. Every cross section of a 3D shape, this was our third question of the day, is circle. What is the shape? And we talked about how sphere is the shape, right? So they proved here that sphere is a three-dimensional figure in which all points of the surface are the same distance from R, right? So this here is even better definition actually of my sphere, because if you know that the center of the circle, this here is my radius, this here's a radius, and this here is also radius in three-dimensional space. So the distance between any of those points, any of those points and the center is always the radius. So this here is R from the center. So the sphere is perfectly symmetrical. So every cross section of a sphere is a triangle, right? So cone doesn't work out because it will create a triangle like so, and cylinder creates a rectangle when cut vertically. So they even used actually my logic, and they drew out in different three-dimensional shapes that have a circle in them. So a cylinder and a cone, right? So they even actually used my logic, and they figured out that this here, a cross section of here would be a rectangle for a cylinder, and a cross section here for a cone would be a triangle. So this here is actually an even better logic than previous answer. I'm going to say great solution and and logic, or I'll just say great solution. So this here takes us to almost 1 o'clock. Again, we did quite a bit of problems here. So again, this morning we did mostly just grade 11, grade 12 kind of math here, and now we're back to kind of grade 8, grade 9, and grade 10 math with mostly geometry questions, but also some algebraic questions as well. So again, so that's going to be the end of my video here. I'm just going to end it just before the hour here. Again, thank you for tuning in. If you were on YouTube and just commenting here, thank you for tuning in, and thank you for watching. Again, I stream basically every single day from Monday to Friday about this time, from about 10, 12, and sometimes at 2. And you can tune in for basically I'm covering a lot of subjects. I'm covering math here. So again, from either grade 9 to grade 12 math if you're in the Ontario curriculum, and if you're in the US, if you're tuning in from the US, I'm covering basically pre-algebra, algebra 1, algebra 2, and pre-calculus and geometry. So these are 5 courses I'm covering with all these questions, and usually my plan is to divide up these videos into simply just pre-algebra, algebra 1, and geometry in one set of videos, and then the harder stuff, so algebra 2 and pre-calculus in another video. And if you're on Ontario curriculum, basically grade 9 video, an hour of grade 9 problems, an hour of grade 10 problems, and an hour of grade 11 and grade 12 problems is how I'm going to kind of filter these questions again. And again, in chemistry as well, I kind of stream chemistry from Tuesdays and Thursdays, and I do basically problems from basically anywhere from grade 9 science to basically university second year level organic chemistry. So that's kind of how I compile my videos here. So again, thank you for watching. If you were tuning in for the first time, thank you for watching. If you were an avid watcher, thank you for supporting me and OneClass as well. And again, thanks for watching, and I'll see you next time in the next video. So have a great day. Stay safe.